they wanted then was something that worked for a small number of nodes, but could scale to a very large number of nodes, more or less gracefully, although don't necessarily want to deliver a system and then grow it from 4 or 8 nodes to tens of thousands. But you certainly want to be able to manufacture parts that can work in both settings. And finally, we wanted to support all known memory models. And I'm not going to go into this, but let me just point out that one of the things that almost everybody assumes when they start out with a multiprocessor, with multiple processors, is that if they do 2 write operations, so assuming that A and B are both equal to 0 initially, but if I write a value of 1 to A, and then I write a value of 1 to B, I hope my notation is self-explanatory, then you might logically assume that if another processor comes along and reads it, so this is processor 1, and processor 2 reads, and it happens to read this one, B, and sees that that's a 1, you might expect that it wouldn't then be able to read A and see the value 0. Right? Well, it turns out, because changing this to 1 happened here, changing this to 1 happened to here, so if this has happened, surely this has happened. In fact, if you look at this, you've got 4 events, each of which have occurred after one of the other events. So you have a cycle there. Right? So that shouldn't happen. At least you would assume that it shouldn't happen. If you look at the way systems are actually implemented, however, this can't happen. And many computers, virtually all computers, in fact, allow something less than what you would nominally assume, which is everything happens strictly in order. So, sequential consistency is simply saying the case where this and no other cases where things get out of order can occur. It's the gold standard when it comes to memory ordering, and it turns out to be the hardest of the different models to support. So, if you can support that, then you can support the weaker models that Intel and nearly everybody else have. So I won't say any more about this, although that was basically the goal here was to support sequential consistency with the assumption that whatever else we have, we can support that as well. Okay. So, now, I'm going to go back. So, now let me go back to the QPI system that I mentioned earlier. I talked a little bit about the link layer. The protocol layer wanted to have directories for a large system. It claims to support that, although it's not explicit what that means. They haven't described actually what directories mean, and there are a lot of variations on directories. They have what they call a home snoop option, which in my opinion is a variant of directories. Basically the idea is that whenever you want to do something, you send a request to the memory node that has the data, and it then sends out messages. Well, it may actually remember whether or not the data is cached, but if it doesn't, it simply sends messages to everybody saying, you have this data, and gets all the responses back, and then sends the results to the home node. This is an idea that actually was published as a variant of directories back in 1984. Intel has chosen a new term for it. They call it home snoop option. And then they have something that they call a source snoop option. And this is actually the only one that they really talk very much about at this point. That's the one that's described in several chapters in this book. And it's the part that, in my opinion, is the most interesting, mainly because I was involved in the development of that. So I'm going to say a little bit about the QPI source snooping protocol, although it was actually developed after I left, and I'm also going to be talking about the protocol that we developed, which was an ancestor of QPI, and say a little bit about the differences. But if you notice, the characteristics here look a lot like what I described to you earlier, which was our 2001 goals, and in fact the differences between those two